Hi, I'm Zheng Yuxiang from UT Austin. I'm glad to present our work, ACID, Action-Conditional Implicit Visual Dynamics for Deformable Object Manipulation. This is joint work with collaborators from Stanford, NVIDIA, and Caltech. From playing with plush toys to making pizza dough, deformable objects are prevalent in many daily activities. Perceiving these objects and modeling their dynamics play an integral role in building autonomous robots to interact with these soft objects. Decades of robotic research have developed algorithms for manipulating non-rigid objects. Such methods have shown success in deformable linear objects, cloth and fabric, and some simple primitive 3D shapes. However, modeling general volumetric deformable objects is still beyond reach. Two major challenges of modeling realistic volumetric deformable objects are partial observability and complex nonlinear dynamics. Deformation can induce severe self-occlusion and make certain parts invisible. In addition, the complex nonlinear dynamics in the infinite configuration space of these deformable objects make the problem even harder. In this project, we studied the goal-conditioned volumetric deformable manipulation. Given a start and goal state observation of a deformable object, we learn a visual dynamics model. With the learned visual dynamics model, we use model-based control to roll out multiple actions that manipulate the object into the goal state. To tackle challenges of partial observability and complex nonlinear dynamics, we introduced ACID, Action-Conditional Implicit Dynamics. ACID takes as input the RGBD observation and the action and predicts the geometry and the dynamics of the object. It reconstructs 3D shapes from partial view and predicts action-conditional forward dynamics. The key idea of ACID is using neuro-implicit representations to jointly represent the geometry and dynamics. Neuro-implicit representations are mappings from a 3D coordinate to quantities at the coordinates. It serves as a unified representation for geometry and dynamics, is continuous and memory efficient, and is end-to-end trainable with multiple supervisions. We use implicit neural representation for occupancy, correspondence, and the flow fields. Occupancy field is a mapping from a 3D coordinate to the occupancy value, whether the point is occupied by the object. It encodes the geometry in the neuro-implicit representations. We encode the dynamics in the correspondence field and the flow field. The correspondence field contains the local feature descriptors. It's useful when comparing predicted deformed object and the goal object. The flow field contains the per-point flow vector, which describes the deformation. Our model ACID predicts occupancy field and correspondence field from RGB observations. ACID also predicts the action-conditional flow field. We represent action as a 3D grasp point and a 3D release point. We introduce our occupancy and correspondence prediction here. We first spec project the RGBD observation into RGBD point cloud. Then we encode and project the point cloud into 2D feature planes. To enhance fine-grained reasoning, we use local implicit representations. Given an arbitrary 3D location, we use bilinear interpolation to query local feature at this location. Our decoder predicts occupancy score and per-point feature given 3D location and local feature. The occupancy decoder predicts the occupancy field and the correspondence decoder predicts the correspondence field. We can supervise occupancy decoder with the ground truth occupancy. To train the correspondence decoder, we need to specify the correspondence across frames. The object is under deformation across frames, so we need deformation invariant metric to determine if a pair of points are corresponded. We employ geodesic distance, the shortest distance between 2 points on surface. The purple pair of points are not corresponded, so the geodesic distance between them is large, although the Euclidean distance is small. The geodesic distance between the green pair of points is small, and these 2 points are corresponded. So we use the green pair as the positive pair and the purple pair as the negative pair. We use contrastive loss to pull the point features of positive pairs close and push away the point features of negative pairs. With geodesic-based contrastive loss, our model can predict deformation-consistent point features to establish correspondence. Let's now introduce our dynamics prediction branch. As presented above, we extract 2D feature planes of occupancy and correspondence field prediction. To predict dynamics from a single observation, we use action as extra input. We combine the back-projected point cloud with action parameters and use dynamics encoder to project and encode them into another set of 2D feature planes. Conditioning on both sets of feature planes, our flow decoder predicts the action-conditional flow field. In conclusion, our model ACID takes as input an RGBD observation and an action represented as a grasp point and a release point, and simultaneously predicts occupancy field, correspondence field, and the action-conditional flow field. To generate training data and evaluate our method, we develop a framework, PlushSim, for volumetric deformable manipulation. PlushSim is a simulation framework with GPU-accelerated FEM simulation and real-time ray tracing rendering. It provides realistic dynamics modeling and observations. We generate our data with PlushSim. We randomize lighting and scene layout and manipulation actions. Altogether, we get over 17K manipulation trajectories. We split the trajectories into train and test set by objects, so we train and test ACID on different objects. We apply model-based manipulation with ACID as the visual dynamics model. We sample action sequences with ACID's occupancy field. Given the action, we use flow field to predict the object shape after deformation and compute the distance between the predicted shape and the target shape with the correspondence field, and we select the best actions based on the distance. We quantitatively evaluate the goal-conditioned manipulation performance of ACID and other baselines. First, we evaluate the pixel flow, which models visual dynamics in 2D pixel space. Pixel flow predicts incorrect flow direction and shows very poor manipulation performance. It indicates that modeling deformable object dynamics requires reasoning over complete object shape. We also evaluate voxel flow, a voxel-based action-conditional visual dynamics model. The voxel representation is discrete and gives noisy and inconsistent flow prediction. This suggests the need of a continuous representation when modeling deformable object and their dynamics. Benefit from the continuous and compact neural implicit representation. ACID can predict consistent and smooth action-conditional flow. In addition, these results are on the unseen test object. ACID can generalize learned visual dynamics to this unseen object. We also conduct a self-evaluation, where we replace the geodesic-based contrastive loss with the Euclidean-based one. With geodesic-based contrastive learning, ACID can establish more accurate correspondence between the predicted and target objects, which boosts the performance of goal-conditioned manipulation. Here we show the qualitative results of manipulation simulation. ACID can predict consistent correspondence field across frames. We also apply ACID to real-world deformable objects. Trained with simulated dynamics, ACID-based model predictive control can generalize to real-world observations and successfully manipulate the object into target configuration. We try some other deformable objects and configurations. Benefited from the randomized training data and the multi-step property of model-based manipulation, ACID can generalize to objects with different appearance and dynamics. In conclusion, we propose ACID, which encodes geometry and dynamics of deformable objects in structured neural implicit representations. To train ACID, we develop PlushSim, an open-source real-time FEM simulation framework for volumetric deformable manipulation. We deploy ACID both in simulation and on the real robot and show successful manipulation results. The key limitations of ACID are that we require 3D ground truth for training, and we don't explicitly model physics from observations, which we hope to address in the future work.